Let's move on to discuss symmetric relations. A relation R defined on a set A is said to be symmetric if for A and B in a set A, okay, A is related to A belongs to R implies that B related to A is also in the relation R. It means that if A is related to B, then B must also be related to what? A. At the beginning of this tutorial, I told you that the pair AB is not equal to BA unless A and B are of course the same. Let's take an example. On this note, I want to bring to your attention that if A is not related to B, then we don't expect to see B relating to A. This is an if statement. If you have P implies Q, we read it as if P then Q. This is an if statement. If this is true and this is true, then the overall statement is true. If this is false and this is true, then the overall statement is true. Again, if this is false and this is also false, the statement is still true. However, if this is true and this is false, then the statement becomes a false statement. So take note of this. And I want you to visualize this in a practical way. Assuming you have a roommate, sorry to say, assuming I have a roommate, this is me, and this is my roommate. If I buy food for my roommate, I expect that he also buy food for me. It means that if I don't buy any food, he also doesn't buy me any food. I'm taking it again. This is me and this is my roommate. If I buy food for my roommate, then my roommate must also buy food for me. But if I don't buy the food for my roommate, I don't expect my roommate to buy any food for me. So that is what we are saying here, that if A is related to B, then B must also be related to A. If you don't see A, B, it means that you don't expect to see B, comma A. And in that case, the relation is still symmetric. Don't worry if you don't understand this. Let's take example and you understand. Assume you have R1 equal to is R1 symmetric? The law for symmetric relation says that for elements A and B in a set A, if we have A relating to B, then it implies that B must also relate to A or must belong to the relation R. These two must belong to the relation R. And so, if we consider the first element here, we have 1, 3. So we are expecting to see that 3, 1 is also in the relation. When we take the second one, 1, 5, it means we are expecting to see 5, 1. Likewise, if we take 5, 7, it means we are expecting to see 7, 5. And lastly, if we take 3, 7, it means we are expecting to see 7, 3. So every member you see, you have to see its inverse. Let's check. We have 1, 3, but we don't have 3, 1. We have 1, 5, but we don't have 5, 1. So the moment one person fails the condition, we conclude that the relation is not symmetric. As well as we have 5, 7, but we don't have 7, 5. We have 3, 7, but we don't have 7, 3. So it means that R1 is not symmetric. Let's take one example. Is R2 symmetric? That is a question to you. So let's say the law of symmetric says that for A, comma B in the set A, if we have A, comma B in a relation, then it implies that B, comma A must also be in the relation. So let's take the elements one after the other. In this case, the first element we have is 1, 1. In checking for symmetric, ignore 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and all that. They obey that rule automatically. So don't even bother yourself checking them. We move to the next item. We have 1, 3. So we have to check whether we have 3, 1. We have 1, 3 here, and of course we have 3, 1 here. So this is checked. We move to the next 10. We have 3, 5. So we check whether we have 5, 3. We have this, and of course we have 5, 3. So this is also checked. The last element is 5 5, and I said that these guys automatically obey the rule, so you don't waste your time on them. So having checked that all these things are present in the relation, it means that we can conclude that R2 is symmetric. Is R3 symmetric? That is a challenge to you. You may pause the video and try to deduce it. Okay, so I said earlier that if you have A relating to A, if you are checking for symmetric and you have A relating to A, don't bother to look for its counterpart. It is the counterpart of itself. So these guys already obey the rule. In the example I cited with my roommate, I said that if I buy food for my roommate, I expect he also buy me food. But if I don't expect him to buy any food for me. That would be a cheat. And if there's a cheat, we say it is not symmetric. So here we have 1 1, it obeys. 2 2, it obeys. 3 3, it obeys. 4 4 obeys. So we say that R3 is symmetric. Because we do not have any two distinct elements relating to themselves, so that we check their counterparts. The reason is we have 1 here and we have 1 here. If I should interchange the position of this and that, it is still going to be 1 1. So the counterparts are themselves. So R3 is symmetric. As we are doing, I keep on reminding you that it is not always the case that you are going to have numbers like this to play with. They can take you into the field of vectors. They can take you into the field of polynomials, the field of lines. In fact, some arbitrary field, and they test you. Whatever be the case, if you are checking for symmetric, let's say if you have AB obeying that property, it means that BA must also obey that property. So you check. If that is true for all the elements, then you conclude that, of course, it is symmetric. The same way in the case of reflexivity, you'll be given a relation in a, let's say, a vector field or a polynomial field or even lines. If they give you the property that A relates to, let's say, B, and the condition A, B, C must hold, it means that if you take an element with itself, you check whether it still obeys the condition. If that is the case, then you conclude. If you check and it does not obey, then you also conclude. We are going to solve more questions of that type.